So thanks so much for having me. It's been fun to be here today and talk to some of the faculty here at the University of Arizona and talk about all the great things going on at Quantinuum. So just a tiny bit about Quantinuum. We are a company based in Broomfield, Colorado, just outside of Denver, focused on building trapped ion quantum computers. And that's amazing that I get to say that. When I graduated with my PhD, I did not think anyone would ever say those words, right? And so after a postdoc, I found myself accidentally employable. There are real jobs for people to build quantum computers and shoot atoms with lasers and get paid for this, which is really exciting. So hopefully I can share some of that excitement with you today. Okay, so why would you build a quantum computer? Well, it turns out that some problems are hard in physics. And they're hard in the sense that all the best methods we know for classical computers sort of break down. So to understand that, let's start with the problem that is not hard. And that's just a regular old magnet. It's got a north end and a south end. And if you were to take that magnet and zoom inside, you would find it's made of lots of little magnets. So domains, where you have a magnetic material that all have some magnetic moment that aligns and sort of gives you your big magnet there. If you were to zoom in more, you'd find it's made out of atoms. And certain kinds of atoms, like nickel, iron, cobalt, they're magnetic. And they're magnetic because if you were to zoom in some more, they have unpaired electrons. Okay, so the physics of why some electrons like to pair up and these little magnets that are my electrons cancel out and why some don't, like an iron, I won't go into that. But just know that electrons are like little magnets. They have a property called spin, and it likes to align with magnetic field. And because electrons are quantum mechanical, I only have to worry about two states. My spin can be pointed up or it can be pointed down. And that's all I have to worry about. Now this might seem counterintuitive to you because you'd say, well, I can have an electron pointed that way. But that's just up plus down with some phase and amplitude to give me that vector in the other direction. Okay? So for quantum mechanics, all I have to worry about is what are my electrons doing? Those are my little magnets there. And if I just have one electron, it can only be in two states, up or down. And I can calculate the energy for each of those. And then everything I need to know about my system I can get from that. If I have two electrons, there's four possibilities. Up, up, down, down, and down, up. So I have two different states. That's my up or down, raised to the power of 2 because I have two electrons. It tells me how many possible states there are. 2 to the 3 is 8. So here's all my configurations for 3 electrons. Up, 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 down. I won't read through them all, but they're all right up there. If I have 4 electrons, then it goes to 16, then 32, then 64, then 128. And it keeps doubling each time. And that may not sound too intimidating. 256 isn't that big of a number. But if I get to 50 electrons, there are just over 1 quadrillion different ways to arrange these electrons. And if I want to calculate the energy for all 1 quadrillion different ways I can arrange my electrons, well, I can't do that with the computer. I don't have enough memory. I don't have enough processing power to hold a 1 trillion or 1 quadrillion by 1 quadrillion matrix to propagate this sort of information. And it gets worse because at 300, that's more possible states for 300 electrons than there are atoms in the universe. So I'll let an astrophysicist tell you how we know there's more than roughly 2 to the 300 atoms in the universe. I think that's amazing that we can know that. I'm just an atomic physicist. But the complexity, just the combinatorics of all the different possibilities that things could arrange themselves is just absolutely staggering. Okay? So you might say, if that's the case, then why can we understand any of physics? And you'd say, well, because most of the time, if I'm talking about magnets, I don't really care what the configuration is. I just care how many are pointed up and how many are pointed down. And from that, I can know how big my magnetic moment is. But for some systems, it actually matters, it turns out, all these configurations and their relationships with each other. So for systems like some exotic forms of superconductivity, or for one of my favorite materials, which is a quantum spin liquid, it turns out these quantum correlations really matter. And these different states between up, up, down, or down, up, up, and the relative amplitudes of those states can really, really matter. And these problems are hard to solve with classical computers because you can't just brute force calculate all the possibilities because there's too many of them. So a nice model for a material is you can say, well, it's a solid, so all my atoms arrange themselves in nice, a grid pattern like I've got up here. That's not always true, but it is true for many things. And then I can have my little electrons, which act like bar magnets, and they can be pointed up or down, and they can hop around along this grid. And this looks pretty, I mean, I can draw it, right? So it can't be that complex. But if I try and brute force solve this problem with the interactions between my electrons, it blows up. I can't do that. So often what we're stuck doing is you say, well, oh, wrong direction on my arrow. I'll just brute force solve some small part of it, and then assume that I can take everything else and say, it just sort of acts like a global field. So I'll take the average of that field, or the mean field here, and sort of apply that as a field that the whole system sits in, and maybe I can understand my system that way. Brute force solve some small part of it, add some mean field correction in from the rest of the things that are further away that hopefully don't matter, and maybe my life works. And this works for many materials. And if you try to solve a problem in this way, what you then do is you make your circle larger and see how your answer changes. And if this is a good approximation, eventually your answer stops changing and you say, aha, now as I make my circle bigger and bigger, I get the same answer no matter the size. So that means the approximation I'm making by throwing away all that extra information is good. But sometimes you make your circle bigger and bigger and bigger, and then your computer stops working because it's too big, and I still haven't converged on a good answer. In which case you say, I need a better way to do this problem. And it turns out for molecules, this can be even worse. Right? So if I have some complicated molecule, this is Fumoko here, and I want to say, how are my electrons jumping around between these different atoms? Each of these atoms has multiple orbitals. I can't brute force solve this problem. And it's never exactly clear what approximations I can make. And these same sort of mean field ideas you could use, where you truncate the information you're keeping, break down pretty quick. Okay, so I don't want to simulate these materials classically. It's too hard. So what I really need is to simulate them quantum mechanically, where this information is natively encapsulated in my computer. Okay, and so we can't have a talk about quantum computing without talking about Richard Feynman. Back in 1981, he realized, before we had quantum computers and before regular computers were all that great, that if you wanted to simulate nature, you should do it with another quantum mechanical system, because nature is quantum mechanical. Okay, and I love this statement at the end. He says, and it's a wonderful problem because it doesn't look so easy. So here, 45 years later, we're still sort of in the beginnings of quantum computing. We're just barely solving problems with our quantum computers you can't solve any other way. So it wasn't so easy, but really exciting. So this idea of a quantum simulation is to say, I'm going to make fake electrons. Electrons that I can control and control their interactions in their environment. And I can program in then how they interact, which is hopefully how they interact in my chunk of stuff I'm trying to study. And I can measure things with my fake electrons and understand how the world works. Okay? Now there's other problems you could solve with the quantum computer. Things like Shor's algorithm for factoring, or Grover's search algorithm, or binary optimization problems, where we expect a quantum advantage. I don't have great physical intuition for these. I can tell you how Shor's algorithm relies on the quantum Fourier transform that's better at these different things, but no real physical intuition for why these systems work. I think for today's purpose, we'll just say some math problems match what a quantum computer can do well, and some do not. Sometimes it's because they map back onto physics problems we can solve, but other times it's just weird math. Okay, so we're finding out more weird math things all the time, and there's lots of applications there. I shouldn't downplay those at all, but for today I'll stick where I'm comfortable, and that's with the physics. Okay, so if I'm going to make some fake electrons and make them interact, we can do this in a couple different ways. I'm going to primarily focus on trapped ions there in the center. I have an individual atom. It's a quantum mechanical object. I rip off one of the electrons so it's easy to grab onto with electric fields, and I can move it around, and then I can shoot it with lasers and make it do what I want. Sort of tune the interactions between it and its neighbor atoms. Neutral atoms are very similar. Now you're holding them in a light field rather than an electric field, so they're a little more fragile, but very similar physics. Superconducting Josephson junctions are really interesting. You actually make little tiny circuits, and then you cool them down to like 20, 30 millikelvin, and then they become quantum mechanical. And they have two states that sort of act like my electron being spin up or spin down, and I can tune the interactions between them using microwave couplers. So these are printed circuits you can make and then put in a dilution refrigerator and have them act like little fake electrons. I also put Majorana fermions up there, which maybe have been observed, possibly. And then also semiconductor quantum dots, where you can have a little well inside a semiconductor, and it's an actual electron, but it's controllable. And then photons are, of course, quantum mechanical as well. But I'll talk about trapped ions today, because that's what we do at Quantinuum. So here we have a picture of our trapped ion quantum computer, the very heart of it. there's this weird looking bow tie thing, that circle and then these two lines, those are electrodes. And those electrodes trap my ions. They hover about 70 microns off that surface, so the width of a sort of thick human hair. And they move the qubits back and forth out of regions where I can shoot them with lasers. Okay, my qubits are barium-137 atoms. So if you can imagine in your mind your periodic table, it's in that second column. So when I rip off an electron, there's really just one valence electron, and that means it's easy to address with lasers. Right? You can choose any atom you want, but this happens to be a particularly good one for the laser wavelengths that exist. I also have ytterbium atoms in there, but they're not a qubit. They're not fake electrons. They're just there to cool down my barium atoms as I do a calculation. As I move these qubits around, they start to get hot, and temperature's sort of weird with a single atom. What I really mean is they're moving more than I want them to. And if they're moving too much and I try and shoot them with the laser beam, that causes errors. So in the middle of the calculation, I can cool that ytterbium atom, which means stop it from moving, and it will cool its barium buddy right next to it, and that allows me to have these calculations go on for a long period of time. Barium is a complicated atom with lots of different states. We're going to ignore them all except for two. So I have two states here, which I'm going to call 0 and 1, or the language before of my fake electron. That's my spin down or spin up, whichever way you like to think about it. And all the other states, both in this electronic ground state as well as electronic excited states, we're going to ignore. Right? And for the most part, we can do that. This is sort of interesting to think about. What this really means, these hyperfine states, whether my qubit is a 0 or a 1, is whether the electron spin, which we talked about a little bit, and the nucleus spin are either aligned or anti-aligned. That's what it means to be a 0 or 1 in my atom here. But it's just a state, and I can read it out at the end. And for the computer scientist programming a quantum computer, it doesn't matter what it is. There's just two states. Okay, so if I want to make a trapped ion, I first send up a neutral atom. I shoot it with a laser to rip off one of its electrons. And once it's ionized, it feels the electric potential from my trap, and it's trapped in a little electric bowl. Okay, it's actually in 3 dimensions, but you can think there's a little electric bowl that holds this ion where it needs to be. And then I can move that electron around by changing the voltage I apply on these little rectangles there, which are supposed to represent my electrodes. So I can move it down to some region where a laser beam is pointed, and then shoot it with a laser beam of a different color now to do a single qubit gate. And what this is doing is it's grabbing my little fake electron here and flipping it from spin down to spin up, or from mostly spin down to kind of spin up. We can control the level of the rotation here that happens on the Bloch sphere, but I control the state of my qubit. I can conversely have 2 qubits in 2 bowls, bring them together into a single little electric field bowl, and then shoot it with a pair of lasers to do a 2-qubit interaction. And the way you should think about this is with my laser beams, I'm pushing on these qubits, but I'm doing it in a way that depends on which state the qubit is in. So if my qubits are both in the spin-up configuration, they both get pushed up from the equilibrium position. If they're both down, they get pushed down. But if they're up, down, or down, up, they get pushed away from each other. And these are charged particles. So if they're further away, that's a lower energy state than if they're right close to each other. And I can use this pushing on my qubits to create an interaction. And I can make what's called a 2-qubit gate from this. So the effect they have on each other depends on their spins. There's math on this slide. Don't worry about that. What I'm saying is that I have single qubit gates, and if you really want to see what that exactly is, it's here. And I have 2-qubit gates, and here's the math that shows what that does. But just from these 2 ingredients, and this is the important part, I can create any other unitary operation I want. This is a complete set, right? So no matter how crazy complicated my molecule is, I can program that in just using single qubit gates and 2-qubit gates. Now, it may be very difficult. If I have an interaction where all the electrons are interacting with each other, it may be many 2-qubit gates to approximate that. Pair up 1 and 2, then 2 and 3, then 1 and 3, then 1 and 4, then 2 and 4, right? You can see how this could get very complex, but I can build literally anything from this set. This also means that if you have any unitary operation you want to do in your weird mathematical algorithm, yeah, I can build that with, again, this universal gate set. So you don't need to worry about, like, well, how would I get 3 qubits to interact or 4 qubits to interact? You can always build those interactions just from these 2 ingredients here, which is kind of cool. We can prove that our quantum computer can do any unitary set, or unitary operation. Okay, so back to our trap. That trap is only a few millimeters long, but our quantum computer is much larger than that. The only quantum mechanical thing in our computer is the atoms themselves. The electric fields that hold them are classical. The light pulses, they're lasers, so they're really cool, but it's still classical light. And so to control all of that, it actually takes something more room-sized. So if you were to put the Helios quantum computer in this room, it would sort of be from here to the wall. It's a big thing. And what that is, here's a nice rendering of the system, the newest version of the system that we're sending to Singapore soon here. It's racks of lasers. I only told you about the laser we use to rip off the electron, the laser for the single qubit gate, and then the two lasers for the two-qubit gate. But there's a lot more lasers. There's roughly a dozen different colors of laser that I need, and I point them to many different places within the trap. So there's racks of lasers. I need electronics to control my qubits, moving them in and out of where the laser beams can interact with them. I need the optics to then shine that laser light onto the qubits themselves. I need a cryogenic system. My qubits are cooled by laser light. They don't need the cryogenics, but it turns out my vacuum does. If I want to prevent air molecules from bashing into my qubits in the middle of a calculation and knocking them out of my trap, well, you do all sorts of things, but one of the things that gets you that last extra mile there is to cool the whole thing down to about 20 Kelvin, where everything freezes out and sticks to the wall except for hydrogen, and then you get really good vacuum pressure. Our vacuum pressure is slightly better than the day side of the moon and not quite as good as the night side of the moon. So pretty good vacuum pressure by the cryogenics there. And then in the very center, there's a ball about the size of a basketball there. It's a titanium vacuum chamber where we suck out all the air, cool the center part of it down to 20 Kelvin, and then shine our laser beams in to interact with that trap. Okay, so here's a picture of 98 qubits in our Helios machine. If you ever had a science teacher tell you can never see an atom, these are atoms. So there's 98 of them. Don't count them, but I promise they're all there. I did count them at one point. And in this system, although this looks kind of weird, that doesn't really look like a computer, it has those same pieces, right? So in the ring there, that circle piece, I can store the qubits I'm not currently using. And I can actually spin that ring around and pull out the qubits one at a time in any order I want as that spins around and load them into this cache region. And then from there, once they're paired up appropriately, because I pulled them out in the order I wanted them to be for these pairs, I can move them down to the quantum logic region where they can interact with the lasers and get those single and two qubit gates. Okay? So individual atoms being moved around, paired up through spinning this ring around and pulling them out in the right order. And if I look at what an algorithm looks like, I can see qubits in my ring being pulled into the cache there. They then wait while I do the gates in this quantum logic region, so you can see the different laser pulses going there. When I'm done with the batch of qubits, they sort down to the end, and then I pull in the next set. So this is really what happens in our quantum computer as far as all of the steps. This is the first depth 1 circuit on a random circuit sampling algorithm here, where you can see it pulls out the qubits just in order because I label them however I want for the first step, and then does these series of laser pulses to do this algorithm. So when you program it in, that's what's happening. This may seem weird, but just think about all the transistors firing in your laptop when you run PowerPoint. I think it's the same level of abstraction. Just this is what I get to have fun with every day. Okay, so if you're a quantum computing nerd and you like statistics, here's it for Helios. We have 98 fully connected qubits, which means any of those qubits at any step in my algorithm can be brought together to do a two-qubit interaction. And because the fidelity of that interaction, which is, you should think about how good it is, 1 minus the error, is very high and doesn't depend on which two qubits I pull together. Here are sort of our error rates: 99.9975 for a single qubit gate, 99.92 for a two qubit gate, and then our state preparation and measurement is 99.95. This is to say that our errors are very low, the best of any commercial quantum computer out there. And these low error rates are important because it allows you to run very deep calculations with still having a low probability of getting an error. So I started by talking about a problem that's very hard because you had to worry about all the different quantum states. So like the hardest thing you could run on your quantum computer is something called random circuit sampling. So I'm going to draw all my qubits up there and then just randomly connect them. And then at the next slice of my algorithm, I'm going to randomly connect them another way and make the most complicated entangled state I could possibly imagine. This is the thing that you really can't solve with any mean field approximations or anything like that. You just have to brute force solve it, which is very, very hard. So on the circuit on the left, time is going to go from the bottom to the top. I run a series of gates. I actually then reverse the circuit in a very specific way so that I can measure at the end and know if I got an error or not. And then I can plot, on the y-axis there is my fidelity estimate, so what fraction of the time did I get the right answer, as a function of how deep my circuit is. And this might seem pretty bad to you, that I'm seeing 40, 20, all the way down to maybe 5% fidelity. I only get the right answer 5% of the time. But it turns out this task for a classical computer to do is near impossible with any fidelity, let alone tens of percent. This plot is weird, but I love it. Pay attention to the light green, blue, whatever that color is. That's from Helios, our 98-qubit machine. You could ask yourself, if I had the Frontier supercomputer, so that's the computer at Oak Ridge National Lab, one of the top 5 in the world right now, and you say, and I do have realistic limits on how much memory it has. I don't assume that it has, an unrealistic amount of memory. I stick with the real limit. How long would it take Frontier to calculate the same circuit? And that's those light green lines. And you can say for our deepest circuit depth, that's 10 to the 38 years. That's insane, right? That is a very, very long time. But our quantum computer does it in a handful of seconds. You could conversely ask, okay, I don't want to do it on a supercomputer. I'll just use it on a GPU. There's this great method to simulate things on my GPU where I get to slice it so I can parallelize it across many, many GPUs. How much power would I need to do that on a series of GPUs? And that's the y-axis on the other side. And you'd say for this GPU slice, that's 10 to the 73 watts of power. If you remember, the sun is 10 to the 26 watts of power. This is more power than all the stars in our galaxy. This is amazing how much power it takes to do on a GPU. Okay, let's just say this is a very hard problem, and you can't do it any other way, which is kind of fun. But it's really just a mathematical problem. But we actually did find a use for it, and that's you can make certified random numbers. There's a lot of text on this slide. I apologize I didn't go back to simplify it at all. But what I can do is I can send a circuit into a quantum computer that's just a little too hard for a supercomputer to do, but pretty easy for a quantum computer can do. So I can send it the circuit. It gives me back an answer in, say, a second. Now, in my own sweet time, I can take that to the Frontier supercomputer and solve that to verify my quantum computer gave me the right answer. Now, it takes days, a week, a month on a supercomputer, but that's OK. I've got time. Now I know what my answer was from the quantum computer. The fact that it was a good answer and it came back quick tells me it was definitely a quantum computer. And if you have an answer from a quantum computer from a random circuit, it turns out you can provably generate random numbers from that output that you got. And so you can generate random numbers without trusting that the person who said they had a quantum computer actually did. You can verify that yourself. So there's this fun paper that we published with some of our friends at JP Morgan Chase talking about how this protocol could work, where you can take this seemingly random circuit thing that doesn't really do anything and generate something of value, which is verifiable, perfect random numbers, which is pretty cool. But what's even cooler than random numbers is material science. Okay, so I'll talk about a problem that exists in physics that we don't understand, and that's there's this really cool material called yttrium barium copper oxide, and if you cool it way down to low temperatures, it's a superconductor, and if you warm it up, it's not. But if you have it warm enough near room temperature where it's not a superconductor, and you hit it with a laser pulse, it starts to superconduct for just a very brief period of time. This has been observed in the lab. There's a paper about it on Nature from 2024 there. It's a well-known phenomenon. They've got some ideas of how this works, but it's really hard to simulate. So perfect candidate for a quantum computer. So we can take this lattice model back. Again, I got my electrons. They hop around. They interact in a specific way. We know a little bit about how these interactions should work in this material. So we can program that in, use our quantum computer to program in a low energy state, but it doesn't have to be the ground state of this system. I can use my quantum computer to create an excitation, which is the equivalent of this light laser pulse that hits it. I can then program my quantum computer to evolve this system as it would in a real material, just evolve it forward in time, and then measure the same kinds of things that someone would measure in a lab. In this case, it's something called eta pairing correlations. It's a particular signature of, hey, is this electron over here messing with this electron over here? And I can measure that and say, do I see superconductivity or not? And this has been done before classically. The largest classical simulations to date can just do 14 sites. And this is a bit of a problem because if you can only do 14 sites, it turns out a lot of this physics can be sort of messed up by stuff happening on the boundary. If you're just studying a small chunk of stuff, you get different answers than if you study a large chunk of stuff. And so Helios is able to sort of more than double that and do 36 sites or 72 orbitals of this system. So a better classical a better simulation than you could do on a classical computer, or at least a bigger one. Okay, so at time 0, I look at these correlations and there's not much going on there. It's just sort of talking with its nearest neighbors and that's it. Exactly what we expect. We hit it with a light pulse. We see it kind of go crazy for a second in that center panel. And then at slightly longer time, we see this interesting checkerboard pattern. Now, I'm not a condensed matter physicist. I'm an atomic physicist. This is way too many atoms for me to understand. But my condensed matter friends tell me this is exactly what we expect to see for eta pairing correlations when you have a superconducting state. Okay, so we can have this system of our fake electrons. These are really atoms, and we're programming these interactions in 1 and 2 qubits at a time, and have it act like a superconductor. And in fact, it even responds to this laser pulse with this itinerant superconductivity the same way we expect for this real material, which is really cool. And this simulation uses 90 qubits, because there's extra you need for state preparation, and has almost 3,500 different 2-qubit gates in this system, right? Which is why those low error rates are so important, right? You can think sort of 1 over this number. If your error is larger than that, then you're never going to get the right answer. But we can get the right answer here. Once you have this simulation working, you can say, okay, now I can start to play with the ingredients and see what's important and what's not. Right? This is like baking cookies and understanding, like, if I leave out the baking powder, what happens? If I leave out the sugar, what happens? Don't leave out either of those things. They're both important. But that's exactly the kind of question we want to ask about these materials, because it's never exactly obvious why this material superconducts and that one doesn't. And we'd like to sort of play around with these things. So we've done a little bit in that direction. There's still a lot more to do. We can add in dopants and then see these bond pairing correlations that match with what we expect to see in theory. But we can really start to play with the ingredients and understand why this material does what it does. And maybe that will give us insights into other materials that can superconduct, maybe at room temperatures, right? I think we're still many steps away from that final goal, but we're starting to understand the physics in a way that wasn't possible with classical simulations. Okay, but to go to larger and larger systems and add in more and more complex interactions, you're going to need lower and lower error rates. And there is going to be some limit on how low I can make my errors, just because my laser pulses are never perfect. And try as I may, there are always going to be some fundamental limit. So we think we can still push on our error rates quite a bit, but then you need to rely on something called quantum error correction, right? So there's a lot of words on this slide, but what you need to know is that physical qubits have errors, and I can lump them together in some mega qubit, which I'll call a logical qubit, that can lower that error rate. If I take that information and encode it across many qubits, then there's ways you can check to see if a single error happened and correct for it and keep going with your calculation rather than having to stop because you just got the wrong answer. Okay, so you can then take these code qubits plus some ancilla qubits and make a more resilient, lower error logical qubit out of it. And that's the era we need to get into, right? There's really cool physics we can do with what we're calling these NISQ quantum computers, these noisy intermediate scale quantum computers, but all the real prizes, understanding real materials, real molecules, doing things like Shor's algorithm, those happen at much, much lower error rates, which no one will achieve without quantum error correction. So I'll just briefly show one demonstration that we did on Helios. We made 50 logical qubits and then did a quantum magnetism simulation there. So this is the XY model. Doesn't matter what that is. We have it on this 2x5x5 bilayer model. We then wrap it around a torus because physicists love to wrap things on toruses. It gets rid of your boundary conditions. So we can simulate this Hamiltonian. And the important thing over here is that if I look about in the purple line, I think that's purple. It looks purple. I see the fidelity, so the probability I got the right answer, go down as I do more and more circuit layers, propagate this simulation for longer and longer time. But then if I encode it in this particular quantum error correcting code, I see that fidelity go up. My logical qubits are now doing better than my physical qubits, to which you should probably say, well, duh, that's what they were supposed to do. But it's actually a really big thing, because not that long ago, nobody could do this. So this is really exciting. It shows we're moving in the right direction. We can now continue to lower errors just by encoding them further in these quantum error correcting qubits. So as we look to the future, we're sort of in the middle of this with Helios, which is 98 qubits. As we look in a couple years, in 2027, Sol will be released. So it's just shy of 200 qubits. We're pushing down the physical error rates a little bit, but largely just increasing the number. And that allows us to build more logical qubits. In 2029, there's Apollo, which is several thousand physical qubits. And then in 2030, Lumos with 1 million physical qubits, which you can get by tiling multiple of these traps together. And each time, even though the error rate on the physical qubits isn't going down by much, or probably from Apollo to Lumos, probably not at all. I think we're sort of hitting the floor there. Because we have more physical qubits to burn, we can get to these really low error rates by encoding larger and larger logical qubits to run more and more complex simulations. So I'm really excited about the future and all the things we can do. And I think that's all the time I've got. So thank you so much for your attention.
Thanks for the really great talk. I have a very broad question, which is that in any, kind of a quantum computing, quantum information system, we have typically two limitations, one being scalability and the other being decoherence. Yeah. So you talked about scalability a bit. Can you say more?
I think it's not on.
Closer.
Okay. Is this better?
I think it's on. Oh, very close.
You have to close really close.
Really close.
Is this better?
There you go.
Okay. Okay. So two things, scalability and decoherence. Would you comment on, as you're talking about scaling up these systems, what's going to happen to the decoherence times? What will be the limiting mechanisms, and how do you think about overcoming those?
Yeah, so with trapped ions, we're lucky in that the coherence times are natively very low, right? I've got these two hyperfine states. If you were to ask the question of how long would it take for one to decay into the other, that answer is like 20,000 years or something. That's not our coherence time. Really, our coherence time is set by the fact that there's some phase that's evolving between these two qubit states, and that eventually gets out of sync with our clock based on, say, magnetic field noise, or slightly changes the level of the energy spacing between these qubits, or other imperfections in our system. So right now we see sort of coherence times on the order of 10 seconds or so. Our gate times are tens of microseconds, and the time it takes to sort of reshuffle the whole trap is measured in, a few to tens of milliseconds. So that separation time scale is very good for us right now. In fact, we normally run out of fidelity when it comes to I did too many gates, which messed up my qubit state. Before I run out of I waited too long and it messed itself up just by doing nothing because of decoherence. So that's nice. I would say as we go to longer and longer simulations, quantum error correction can also help with that decoherence, right? It's just an error like any other, and you can correct that with quantum error correction, with some caveats about leakage, but we know how to fix that too. So I'd say, the dominant error source right now is those two qubit gates, and because in these quantum calculations, you're sort of constantly using these gates to actually move the algorithm forward, or doing these parity checks that let you do your quantum error correction, that's going to be the limiting factor for trapped ions. And the errors from decoherence are sort of roughly an order of magnitude lower, and so and they're also corrected by the same error correcting techniques.
Thank you.
All right, then I guess I'll ask about the scalability question. So what is sort of the limiting right now? I mean, these are clearly micro or nano fabricated, so you can make lots of qubits, but what's limiting you to 98 or 100 and 92, etc.?
Yeah, so there's lots of barium atoms in the world, despite barium-137 being hard to get a hold of. It's an interesting isotope. But, so it's not a problem with the qubits, and we can make as many qubits as we want, they're all perfect. So it's all that environment. So why we stopped at, roughly 100 in Helios, there's lots of technical reasons, but mainly it's about the laser control, right? I only wanted to put laser beams in this case, 8 different spots, so I can do 8 different gates in parallel. And then this was a reasonable size that allowed me to still have all the optical access I needed. As you go larger, you either need to address more spots in your trap, which we are doing with Sol and Apollo, so just brute force your way through the classical optics. And you need to build bigger traps. So these are microfabricated devices, largely using sort of standard CMOS techniques, although there are a few special steps at the end there to get like the top metal layer is nice as we need it to be. So we're working with our fabrication partners to be able to build bigger and bigger systems. We've already built systems that are significantly larger than Helios on the same scale, well, larger than Sol even. We're building up to this sort of Apollo scale. But we think, the nice thing here is that our qubits are the only quantum mechanical thing, and everything else is building the classical control. So can we engineer larger microfabricated systems? I think so. If you look out there at like what's being done and fabrication facilities, they can make chips with very high yield that are sort of multiple centimeters by multiple centimeters. And so that's large enough we can then start to tile those to get to these very large computers.
How large is the chip right now?
The entire package is about an inch square, but just that trace is 3.5 millimeters long. From like sort of the tip of the circle all the way to the end of those two legs.
I have a 9 question. So, like you showed this, like for the Helios, this ring storage from which like you call out the atoms and then like you do gates on them. How do you label like the qubits? Like if I want to do an interaction between qubit number 6 and qubit number 21, like are these differentiated by the wavelengths at which they respond? Like how do you actually label these things? Because they're indistinguishable as ions, right?
Yeah, so completely indistinguishable. If you were to ask which one was which, you couldn't tell. But it's just like that game in the park where the guy takes the 3 cups and then puts the ball under one and then usually tries to cheat you out of your money, right? But if you're watching carefully enough and there's no trick with the hole in the cup or anything like that, you can track, okay, it's in this little electric bowl, I moved it over here, then back again, and you can track where it goes. And so it's all just held in the software. Like I applied these waveforms or these voltages to my trap, and that dragged that qubit number 74. We know where it's at all times just through the classical tracking.
You talked about all these great simulation applications as well as, of course, computing, doing calculations with atoms. How about sensing? Can these devices be useful for, pushing limits of sensing in directions that we haven't thought about before with as many entangled qubits as you have?
Yeah, that's an interesting question. When we do our calibrations, we are now starting to use entangled states to do those calibrations. So you need to measure, is the magnetic field exactly what I want it to be? And if not, feed back to that, because you'll be tracking your qubit frequency all wrong if it's not. In fact, very early on, we had one night where we were bringing up our original H0 system or the H1 system, and the data was terrible. The qubit frequency was all over the place. We didn't know what's going on. We were complaining about this in one of the chats, and our friends in Minnesota who had a similar system said, we saw the same thing. And we overlapped the data, and they lined right up. And then someone had the idea to check the solar weather from the National Oceanic and Atmospheric Administration, and the solar flares that were happening that night and causing the northern lights. Well, it turns out that's currents running through the ionosphere, and that was creating a magnetic field that our qubits were picking up, right? So we use them to sense things, but just so we can cancel them out, right? So our quantum computers are sensitive to things, and we wish they were less sensitive. So we do these calibrations, sometimes using entangled, most of the time not, but every once in a while we'll use an entangled state for a series of calibrations to sort of level things out. If there's additional applications beyond calibrating our quantum computers, we're not pursuing those right now, but they're certainly sensitive probes.
Here's a quick follow-up.
Yeah.
How large of an entangled state you can get?
Yeah, so on all of our systems, it's been the case that we can entangle all of the qubits. So here we've created a 98 qubit like GHZ states. That's a superposition of all spin up with all spin down, and you can see that's better than sort of 90% fidelity.
Yeah.
So you talked about like simulation applications and like just math problems, but kind of in the trajectory, like as you're scaling up your hardware, when in your mind, when do you think like you will hit a commercially relevant application, and would that be a simulation, like a materials thing, or would it be something else? Would it be a surprise, or is there a consensus on where we expect the first true quantum advantage to actually come up?
So I would say right now we have quantum advantage in the sense that I can do some problems you can't do on a classical computer. This random circuit sampling, Google showed that way back in like 2019. right? And would say this is along that same vein. I would say we can even do simulations of sort of physics models that you can't do any other way. I didn't show it here, but even on our H2 machine with 56 qubits, we did some simulations of the Ising model, where we showed next to these phase transitions where all your normal matrix product state sort of methods break down, we can still get the right answer, which is sort of exciting. So quantum advantage in a very limited sense of I can do physics and math problems that maybe are exciting. I think as we get bigger and bigger, the sphere of like problems you could think to address gets larger. And now we're going to be starting to solve problems that aren't just, technically I couldn't solve those before, but I'm actually learning new physics from them. And I expect to see that, continue to see that on Helios as well as with Sol. As we start to get even larger, now you're talking about with a handful of logical qubits, 50 or more, you can now get deep circuits and start to study very small molecules, start to study more complex physics things, where these models are now starting to approach what a company might worry about when they're trying to decide what materials to pursue for a new magnetic medium or something like that, right? So I think it's a slow turn on there. By the time you get to Lumos, where you have several thousand logical qubits with error rates in sort of 10 to the minus 10, 11, 12 range, there I think everyone agrees that there's widespread quantum advantage for chemistry, materials, potentially even optimization, but that's still an open question, as well as things like Shor's algorithm start to happen at that scale. But I think you bring up an interesting point, like there's also going to be surprises along the way, right? We're very interested in an application called quantum topological data analysis. Large sets of data have these weird topological properties. We're not really sure what they're good for, but man, they look interesting, and there's efficient quantum algorithms to solve these. I think that's one area I expect to be surprised, where this will find applications where none exist today. But, I won't bet anything on that, right? It could just be cool math forever, but I think there's lots of different things. And if you look at like the advent of classical computers, you saw the same thing, right? The first application for the transistor was the hearing, because it was the first place where side wave power really, really, really mattered, right? But I don't think anyone invented the transistor thinking, I'm going to build a better hearing aid for this. It was just an application that came along the way. And I think those early Bell Labs pioneers would be just absolutely surprised by all the AI that's going on now. So I totally expect to get surprised, and if I knew by what, then it wouldn't be a surprise, I suppose.
So I'm not sure you can answer this
Okay.
question, but
Always
I'll
ask.
try it anyways.
Yeah.
So how many systems do you guys have deployed, and like who are the type of people actually using them right now? And then sort of a follow-up to that, if somebody here is interested in getting access to doing things with your systems, is there a process for doing that?
Yes. Yeah, so I can totally say how many systems we have. Our original H1 system has been retired, so that's now being used as a test bed in our labs there. We have 2 copies of our H2 machine. Those are both in Colorado, and you can access them through the cloud from anywhere in the world. They're being used by researchers, some paid access, others academic collaborations. We also have 1 copy of our Helios machine, also in Colorado. It's got 98 qubits. We have another machine which is dedicated use for RIKEN, which is the Japanese national lab just outside of Tokyo. It's on premise there. It's owned and operated by us, but specifically for them. And then we are deploying a second copy of Helios to a lab in Singapore later this year. So that'll be the second copy of Helios. And similar to Japan, it'll be dedicated use for Singapore there. And so there's a couple ways you can get access, right? We have paying customers who sort of pay for access. But one of those is actually really useful for you, which is Oak Ridge National Lab. They have something called the Quantum Computing User Program. And so anyone can go and submit an application, say, here's the problem I'd like to run on a quantum computer, and they can grant you credits on our quantum computer through their access that they've paid for there. The same way you get access to like the Frontier supercomputer if you wanted to run some large-scale simulation. So I'd say that's probably the easiest way. But then we also do direct collaborations with different academic groups and startup companies where they come directly to us and we work on a project together. Sometimes that's got an application in mind. Sometimes we're just going to publish a paper. Sometimes it's just neat. But yeah, there's lots of ways to get access to the system.
So I think you have a mixed audience from like different backgrounds. So like in the interest of them, like so there's all these like quantum masters, PhDs that that work at Quantinuum to do this stuff. But could you shed some light on all classical skills like engineering, material science, the kind of skills that you need, and how people from even non-quantum backgrounds can contribute to this endeavor?
Yeah, so when we first started, it was largely a bunch of physics PhDs. Because if you've ever met a physics PhD before, we're very conceited. We think we can do anything, and to some extent we can. I can be a really bad electrical engineer. I can be a terrible mechanical engineer, but I can muddle through, right? And so we built the first generation of tests, and then we realized how bad we were at these things, and we hired a bunch of engineers who were actually good at those sorts of things. So we hire a lot of electrical engineers, a lot of mechanical engineers, material scientists, as you said. Optical engineering is its own field now, right? It's not just physicists who like to play with lasers, but people really trained in this stuff, working on both classical optics, like lasers and beamlines, but also integrated photonics. We hire a lot of systems engineers, people who are experts in sort of saying, for this very large, complex system, how do I break it down and make sure that we can chunk the work off into, bite-sized pieces, and everyone knows where their boundaries are and can make sure that everyone's building something that's compatible in the future. We have technicians who are really, really good at assembling things. There's all kinds of skills that we're pulling in. And of course, there's all the other things you need in a company with HR people. That kind of stuff, which is maybe less interesting to me as a scientist, but also important functions there. But I would say any sort of engineering is something we need. And the important thing is we need people who are sort of curious and willing to invent new techniques to do things.
Maybe you can elaborate a little more on the proportion of, say, PhD level, master's level, bachelor's level that you're hiring.
Yeah, if I look at just the technical staff, so we ignore HR and all that, finance, all those other important but less exciting things, at least to me. I would say we're now roughly 50% PhDs, and the rest are sort of masters and bachelors. But as we continue to build out our engineering orgs, that I think that's the PhDs will be in the minority soon, right? So it's important early on to be really heavy in that research, but especially another one I forgot to mention was software engineering. We have a ton of software engineers. It turns out from all layers of their software stack, the people who are writing the code that directly talks with the hardware, the people doing the compilation of quantum algorithms, to the layer that people submit their circuits on and gives them the results back. There's a ton of software engineering that needs to be done at all levels. And so we're going to see more and more, or less and less PhDs and more engineers.
Actually, speaking of, even within the physics / I would say EE PhDs, people who have studied and have some expertise within quantum areas, I think there's a very different, there's kind of a dichotomy there too, which is the physics PhDs are trained more in the conventional, textbook quantum mechanics of hydrogen atom and particle and potential well. On the other hand, if you go to an EE department where Narayanan might be teaching, quantum computing from Nielsen and Schwann, so these are two very different ways of studying quantum physics as we go through our education. What's the ratio of the physics quantum physicists to, I'd say, the quantum information quantum scientists?
It depends a lot on the group. I would say most of our experimentalists really come from a strong physics background, just because that's where you get a lot of that experimental knowledge right now in academia. Right? People who trapped ions in their PhD or did cold atoms or things like that. BECs, these are really relevant skills, although not exactly what we're doing. If I look more at our theory teams, the people coming up with algorithms, the people thinking deeply about quantum error correction, I would say the majority of them are coming more from this sort of applied, sort of
Quantum information.
quantum information sort of. We get people with degrees in math rather than physics, and I think that diversity in where we're pulling our people has really helped us. These different fields think of things slightly differently, and usually that's helpful.
Yeah, and it's great. I mean, in your talk, it's quite, it's integrating both of these views in a beautiful way. So, yeah, it's really cool.
Great. Thank you to the panel. Yeah, thank you again to the panel. Any questions from the audience?
Brian, you mentioned quantum computer access all seem to be more for research. For research. But I know for a fact that Microsoft used, what about quantum as a service? Microsoft obviously used Quantinuum computers primarily, if not exclusively, for a while. I don't know if that's been decreased, and then AWS has essentially everybody. And so what I'm getting at is for non-research reasons, for engineering, algorithm of development privately or whatever else, can't we access Quantinuum computers through quantum as a service as well?
Absolutely, yeah. So you can access our quantum computers through Azure Quantum directly from us, right? So we have, one of our customers who's very, very open about that is JP Morgan Chase. They have a large research group, right? I find it unlikely that they're running any of their production code through our quantum computers today, but these researchers are figuring out what they need to know to use quantum algorithms in the future for their financial use cases, right? So we do see companies come in. I would still say, from my perspective, what they're doing is research, but it's their applied research for their particular business use cases, right? We see materials companies, we're starting to see more from pharmaceuticals or aerospace sort of industries, yeah. But absolutely, you can get access for those things too.
Speak loud, please.
I just had a quick technical question. So when you move to a 2D trapped ion grid, one of the sort of advantages of a trapped ion system from an error correction perspective is all-to-all connectivity when it comes to the gates. Or you have that sort of pseudo all-to-all connectivity. But that's going to become harder than in a ring topology to do when you have two-dimensional connectivity, because the probability of you being able to, let's say, entangle gate A and gate D on the other side of the chip is going to drop. What's Quantinuum doing to sort of mitigate that? Because since you're using this sort of electric motional mode to be able to do that, and that's going to be pretty hard to scale.
Yeah, so as your trap gets bigger and bigger, the average distance between any two random qubits you'll want to pair up gets larger, and that time it takes to pair them up also becomes larger. So I think that's what you're saying. If you could go to 3 dimensions, that'd be nice, because then you could decrease that distance. For technical reasons, that's pretty difficult, right? Building these complicated electrode structures in 3 dimensions. I won't rule it out, but I'd say it's difficult. So 2 dimensions is nice because it also gives you one direction to read out your information as well. So we're largely stuck in 2 dimensions. I would say for the simulations we're doing of systems as large as Lumos, so a million physical qubits, we're now this sort of, it's a macroscopic, tens of centimeters on each side sort of chip. You can move these trapped ions very quickly. And so the time it takes to do arbitrary connections, even from remote parts of the trap, isn't a deal breaker. It's not longer in our coherence time, but you do start to pay a penalty for large distances. There's a couple ways you can deal with this. You can deal with this algorithmically by saying, if I can look forward in time and know this is coming, I can pre-distribute entangled pairs and then teleport that gate. Similarly, if I can look forward in time and see this gate is coming up, while I'm doing all the other steps of my algorithm, I can classically compile this so those qubits are drifting together. But it turns out there's a lot you can do there. And so I'd say there's a lot of these classical techniques that have to come in through your compilation to sort of minimize those time penalties. But I don't see any reason why we can't scale to tens of millions or even hundreds of millions of qubits before this time penalty becomes, very, very prohibitive. And then you could think about remote entanglement through photonic links or things like that. I mean, these are traffic problems, right? How do I get things across the dense grid, right? And so comparing things to Manhattan when I'm talking about traffic is probably not a good idea, right? But that's because people make dumb decisions in cars. These are ions in regular patterns. A two-dimensional grid is actually a fairly efficient way to route traffic. But even still, eventually you say, I'm not going to drive through the downtown of Manhattan. I need to take a freeway, or I need to hop on an airplane. And so eventually those things do start to come into the architecture, but beyond a million physical qubits. It's sort of from our current analysis. Did that answer the question?
Yeah, it does.
Great.
One last question.
So you don't think there will be a problem until 1 million qubit to connect this system? And how big of a system we're looking at, like physically? how viable it is to build it, use it?
Yeah, so
Repeat the question, please.
yeah, so the question was, okay, I said I don't see any scaling issues to get to 1,000,000 qubits. Is that the limit? And then how large of a system is that? Right? I would say, there's a bunch of sort of natural inflection points. Actually, I think Apollo is sort of the edge of where you can get with classical bulk optics, and then you need to go integrated photonics to get beyond that. That's the big step between that and Lumos. And it also goes to where you start tiling traps rather than having one monolithically, manufactured device. I think you can use that same model that's being used in Lumos to get quite a bit larger before you run into like the next fundamental sort of hurdle. And I'd say our analysis isn't complex enough to clearly identify what that hurdle would be. As far as the device itself, just the ion trap portion is still measured in sort of tens of centimeters across. It still fits in a vacuum chamber that's sort of less than, around a cubic meter and can fit on an optics table, although I don't think you want to put it on an optics table. All the other infrastructure, all those lasers, all the electronics, those start to get quite large, depending on what you assume. If I take the lasers today for Helios and just say, I'll just make a bunch more of those for Lumos, you'll find that one, that is a bad idea, and two, it starts to fill rooms, like this. But there's a lot of room for miniaturization and optimization on the engineering front, and so we're pushing out those. Right? Really, we're taking scientific equipment that hasn't been optimized at all for size, weight, and power, and we're saying, okay, we should probably start thinking about that now, so we can fit this in a reasonable sized room when it comes time. And we can produce one for a reasonable amount of money. But there's a lot of engineering that needs to be, that will be done to bring those costs and those sizes down.
Okay, let's thank the speaker and the panelists and the.